Hey everyone, today we're going to talk about vectors in R3 or 3 space. Just going to take some of the stuff we know from vectors on the Cartesian plane and just add a third dimension. So let's get started. The reason we need to do this is things like force, velocity, other vectors involve a third dimension, especially people taking physics. Physics doesn't just occur on a flat surface like a piece of paper. We're all moving around in 3 dimensions. So today we're going to develop a Cartesian system to represent 3D points and vectors. And we'll also talk about how to extend things like the dot product and adding vectors, etc., from 2D to 3D. And you'll see it's actually just a pretty natural extension to add more dimensions. So to get warmed up a little bit and to get some context and hopefully just, so for some of you guys, this spatial awareness for R3 will come very naturally. And for some of you guys, you'll have to wrestle with it for a bit. I myself I recall having to wrestle a little bit. And then at one point, it was around my second year university, I was doing a multivariable calculus course. It just kind of snapped in and it was like, okay, it just makes sense. But it took me a while to be able to easily visualize things in 3 dimensions. So you're going to have to I know we haven't been in our regular classroom for a while, but see if you can teleport yourself back there to our classroom. And imagine our room is as a 3-dimensional coordinate system where the points are given by, instead of ordered pairs, ordered triples. You have an X value, a Y value, and a Z value. And so we'll say that where our door is usually here. And for those of you guys who are just stumbled upon this on YouTube, like our classroom door is kind of like, it's not perfectly in the corner, but just for the purposes here, imagine the door is at the front corner. This is the origin. This is 0, 0, 0. For the purposes of this little exercise, we could say that this room we can maybe say it goes maybe like 10 meters towards from the front of the room to the back, from side to side, maybe 8 meters, and from the floor to the ceiling, let's use, I don't know if this is true or not, but let's just use 4 meters. So just imagine the room is like 8 by 10 by 4 meters. And we're gonna do a little exercise, seeing if you can figure out where certain points in the room would be using this new system. So the X value is kind of like the distance from the front of the room. The Y value here is going to be like the distance from the left wall, from like your perspective of a student and what we're looking at now. And Z would be, since 0 is on the floor, this is the distance from the floor. So having set all that up, and hopefully you can kind of visualize our room, let's try a couple. So I've got a smaller visual of that at the top. I have some positions here, and I guess in this, normally I have some spots for random points, and I just walk around with a tennis ball and place it there. That's not going to work here. Yeah, where is the order triple for each spot? Now, for some of these, for many of these, you'll be able to give, not an exact, but if we all base it on how big the room is, 8 by 10 by 4, well, we all should have the same answer. But in a case like these bottom ones where I picked on Emily because Emily basically sits like, I recall, sits like around the middle of the room. So, and those ones we might have different numbers, but the spirit of our answer should be the same. So if you want to take a few minutes and think about what these ordered triples would be, you can write them as points, round brackets, X, Y, Z. You can give it a go. Otherwise, I'm going to kind of go through these right now. So the front left bottom corner of the room front, left, bottom was here, and we established that was basically the origin in 3 space, 0, 0, 0. The front left top corner of the room. So front, 0, left, 0, but now I've moved to the top corner of the room, and we said the room was 4 meters tall. Let's go to the front right bottom corner of the room. So for the front right, so I'm at the front still. I haven't moved from the front, 0, but I moved to the far right, 8 meters. And I'm at the bottom, so I'm on the floor, 0. Front right top, so I'm at the front, so 0. I've moved to the right to the corner, 8 meters, and now I'm at the top, 4. So that would be like up here, right? I've moved 0 in the X direction, I've moved 8 in the Y direction, and then 4 in the Y direction, in the Z direction. So Emily sits kind of in the middle of the class, so answers may vary here, but maybe you said maybe she's like 3 or 4 meters from the front, and maybe 3 or 4 meters from the wall, and then on the floor beneath her desk would be 0. I might actually do the same one here on the ceiling. It would be 4, 4. That's where her room location is, X and Y, but the ceiling would be 4 as well. Let's go to the back left corner of the room. So if we go to the back, we said the back of the room is 10 meters from the front, right? And we're at the left, 0. At the bottom would be 0 as well. Back left top, so we're back. We haven't moved to the right, but we're at the top of the room, 10, 0, 4. Now we're going back right at the bottom. So we go to the back 10 meters, to the right 8 meters, and we're staying at the bottom. And then back right top, 10 meters back, 8 meters to the right, and then we're going up 4. So it's my hope that that little exercise and visualizations with this a spot we're kind of all used to seeing can help you wrap your mind around points. Maybe as a little bonus one, this is doable for people that go to our school normally. What do you think of what point would represent bronze door? Like the floor. It's out of our classroom, right? It's kind of, if you think about it, you could walk out our door and go right to Mr. Braun's door. Take a pause and what do you think? So in that case, you wouldn't be moving from the front of the room. You'd actually be going back in like the negative X direction. So if maybe the hallway is like, say, 3 meters wide, Mr. Braun's door would be at a point like this, -3, 0, 0. So the space we're looking at right now is actually only 1/8 of 3 space where all the values are positive. So we need to kind of talk more about that. Let's talk about 3 space. So it can be a challenge to take a 3D concept and draw it on a 2D piece of paper. So we're going to get some practice doing that. And by convention, we set the X, Y, and Z axes when we're drawing R3 or 3 space on a piece of paper as the following. We have the Z direction pointing up, and our Cartesian plane, we've kind of like flipped on its side and rotated a bit so that the positive X direction goes out this way and the Y direction goes out this way. And the directions we choose for positive obey a right hand rule. So if you stick up your thumb and curl your right thumb and curl your right fingers, they go from positive X to positive Y. So X coming out to the left this way, fingers curl to the positive Y direction. 3 space, as I mentioned, is broken up into 8 we call octants. The Cartesian plane is divided up into 1, 2, 3, 4 quadrants. But when you add an extra dimension, that doubles, and now you have 8 octants. And the Cartesian plane is separated by 3 lines. In this case, the R3, or the Cartesian plane is broken up by 2 lines. That divides it up into its quadrants. Lines don't chop up 3 space, planes do. You can see we have 3 planes here that chop R3 up into 8 octants. And so the XY plane is this guy here. I'm just going to do a couple extra things here. I kind of forget if I cover these later or introduce them maybe in a different lesson, but it's not very complicated to go over. If you think about any point on the XY plane, it's going to have an X value and a Y value, but it's like the floor of our classroom. If you're on the floor, you're not going up any. At any point on the XY plane, the Z value is 0. So we can actually state the equation of that plane. The equation of that plane is Z equals 0. At any point on that plane, the Z value is 0. The next plane we can talk about, let's talk about this guy here. Where should I put this? Let's go up here. This guy is the XZ plane. So that was kind of like the left wall in our classroom. Any point on that plane has an X value and a Z value, but the Y value is always 0 because you're not moving left or right off of that plane or that wall. And the equation for that plane is Y equals 0. And then lastly, we have this YZ plane. And all the points there have an X value of 0. And so appropriately enough, the equation of that plane is X equals to 0. So a little introduction into how we break up R3, and what we need to do today is kind of get practice, maybe plotting some points in R3 and getting used to all these conventions. So I think we touched on this. If you think about our room, right? Our room was where's my cursor? Our room would be like the front, right, I'll say upper octant in R3. If you think about the room, if you can just visualize, this is like our room here. The exercise we did earlier, all the X, Y, Z values were positive. So this is the front of R3, the right, and the upper octant. The XY plane, we talked about this, would be the floor. The XZ plane was like the left wall. And the YZ plane would be like the board, like the whiteboard at the front of the room. So again, just another little exercise, getting used to wrapping our minds around R3. Let's plot our first point. So we're going to plot the point 2, -3, 7. So this is the one time a year I do this as well. So it takes me a few minutes to get warmed up, and I did not plot these points ahead of time. So we'll do it together. So start at the origin, and we're plotting the point 2, 3, 7. So, and there's no scale on these. It's kind of hard. Adding a scale does make the diagram a little clustered, as you can see here. So sometimes we might use it, sometimes not. But in the case of not, from the origin, we kind of just go 1, 2 in the positive x-axis, and then we are going -3. So +3, we would move to the right in the positive y direction, but here we're going to move to the left, like 1, 2, 3, like that. So 2, 3 to the left, and now 7 is in the positive z direction. So 1, 2, 3, 4, 5, 6, something like 1, 2, 3, 4, 5, 6, something like that. And here we go. This would be the point 2, -3, 7. And you can see it's in the front, it's in the left, and it's in the upper quadrant, or octant, excuse me. Now, for some of you, you'll be able to see, yeah, I get that what octant that's in. For others, it's going to take some getting used to, and you may wish to choose not to do this. I might just use a different color so it's easy on here. Sometimes drawing a 3D box can help you visualize where you are. So here, I'm going to take all the stuff I did. Oh, it's green, so it's hard to see. I'm going to take that and make a box out of it. And now finishing off that little 3D sketch, you can kind of see, oh yeah, that's like, I can see how that's out in front and left and above the XY plane. As I said, this takes some getting used to. So if that didn't sink in right away, you're going to have to let it digest. We'll practice drawing a few more points. It'd be great if I was there with you to give a bit of a guiding hand. But this is the best we can do for now. So yeah, let's just plot some more points and try to let it sink in a little bit. So in terms of visualizing, can you visualize which octant each of these points is located in? So use the language front, back, left, right, upper, lower, or top, bottom. If you want to pause the video and unpause when you think you've got it, that's great. Or you can just follow along with me here. And I'm just going to switch to that color. So in terms of top, bottom, I think earlier I was using upper, lower. So I might continue to use that language, upper, lower. All right, so 1, 2, 3. If you said front, right, upper, then you've got it. And you guys are you so used to the Cartesian plane? You guys usually know that, you know, to the right is the positive X direction, and, you know, up is the positive Y direction. If you can just get used to now the positive for the X value means you're moving out front, then you're pretty much the signs tell you where to go. For B, that -3 means we're going back into the page, you know, back this way in the negative X direction. But a +2, +1 means we're moving to the right in the Y direction and up in the Z direction. C is the opposite of everything from part A. So we'll be moving back first and then left and then down to plot our point. And then finally in D, we'd be moving to the front in the positive X direction and then to the right and then down. We won't plot these ones right now. We're going to plot some more points in the next example. So some of these points will lie on a plane or an axis. And so in that case, can you describe the line or the axis that it's on, or the plane or the axis it's on, or just plot the point. So at this point, it might be good for you to pause the video and try to sketch these on your own and then unpause when you're ready. Or you can follow with me. So 2, 6, 1. So 1, 2, 6 in the positive Y direction. This time I'm going to the left. So like 1, 2, 3, 4, 5, 6. I like adding these ticks. It just helps me. 6 and then up 1. So maybe here. And this is the point A, 2, 6, 1. And if you'd like, you can, if you're feeling adventurous, you can make this into a box. That goes there above. That goes back there. No, wait, go something like that. So just, again, that's a really super rough sketch, but you can now visualize it's out front. It's to the right. And it is above. Just like our classroom. Let's try B, 0, 0, -6. So B is a bit easier. So 0 in the X direction, 0 in the Y direction. We're still at the origin, but now we move 6 in the negative Z direction. It goes down here. So something like this, B, 0, 0, -6. That is on the Z axis. And it's actually on the negative Z axis. That's where that point is. Let's try, oh, that's not really A and B. I guess I'm just saying that's the first point, that's the second point. Now let's go on to C2, 3, 0. So we move 2 in the positive x direction, 1, 2, then 3 in the positive y direction, 1, 2, 3, let's say, not to scale. And that's our point. That's point C2, 3, 0. Now I haven't moved up or down, right? So if you can envision, it's like I'm on the floor of like our classroom. I'm on the XY plane in this example because the Z value is 0. And finally, D, -1, -3, -4. So from the origin, I'll go back 1, 3 to the left, so like 1, 2, 3, and then 4 up. Something like that. D, -1, -3, 4. I'm going to try my best here to make a sketch here of what this looks like as a box. So if you can't draw a 3D box, that's okay. But maybe completing the box helps you kind of visualize, yeah, okay, I get it. I'm back. I went back in the negative x direction. Then I went to the left, and I went above the XY plane. Again, just do your best. If you don't like drawing the box in, if you can figure out the octant by just looking at the signs, you're fine. All right, so hopefully now you're a little bit more comfortable about 3-space or R3. Now we're going to talk about all the work we did with algebraic vectors in R2, and what does that mean in R3? And actually, a lot of the stuff stays the same. So if V is a vector in 3-space, if you pick V up so that its tail is at the origin, you have a position vector. And this is exactly the way we defined algebraic vectors and position vectors in R2. So if you want to talk about the vector going from the origin to some point P in 3-space, you just use this notation here, square brackets, and you have your x value, y value, in this case, your z value. So this vector would be the vector that goes from the origin to point P, x1, y1, z1. And it's really helpful if you use, if you're describing a point, you use round brackets. If you're describing a vector that goes from the origin to that point, use square brackets. So if you recall, like, none of this is different than 2D, except we just have an extra dimension. What about all our properties, operations? It's all basically the same. So x, y, z can represent any vector in R3. It covers all the bases, allowing negative x values, negative y values, negative z values. You can get anywhere in R3 using this notation. And just like in R2, you can write a vector in 3-space using building block vectors, but we have one extra unit vector now. The vector in the positive x direction, the unit vector is vector 1, 0, 0. I think you would all agree that that vector is 1 unit long. In the y direction, we have 0, 1, 0, and now we have a third dimension. So we have a third building block unit vector, 0, 0, 1. And you could take this to as many dimensions as you want, 4 dimensions, 5 dimensions. Those unit vectors would all just have zeros and a 1. So I could write a vector, say, let's say that vector A is A1, A2, A3. Then I could write that as A1 times I hat plus A2 times J hat plus A3 times K hat. I can write it as that linear combination. This is just like R2. Now we have the extra third unit vector. And I do like having my caps on my unit vectors. I know your diagram doesn't. It's okay if you don't. Next property, vector addition. So say you have two vectors, A1, A2, A3, and you wanted to add another vector, B1, B2, B3. Well, just like with R2, you just add the components together. Again, everything is the same. It's just now you have a third dimension. And you also now know how to add vectors in any dimension. You just add their components. Scalar multiplication. So some vector scalar k times a vector, a1, a2, a3. As we know, that would just go onto each ka2, ka3, just like R2. Nothing has changed. The dot product is the same. But now you have vectors in R3. So if you want to dot vector A, I guess maybe I should say here I'm using A as A1. You guys have probably figured this out. Another vector I'm calling B is B1, B2, B3. But if you want to dot two vectors together, B1, B2, B3, we apply the same rule as in R2. You just multiply the components together, A1, B1, A2, B2, A3, B3, and add them. It's the same. If you wanted to describe a vector from one point in R3 to another, so let's just say I have some vector that goes from A to B like so, and I want to describe that guy as a position vector. Excuse me. How do we do that? Well, we, just like with R2, we subtract the coordinates. So to get the x value, I do B1 minus A1, and then B2 minus A2. We would have stopped there in R2, but now we have a third component, a Z, B3 minus A3. And the magnitude of that vector would just be like a 3D Pythagorean theorem. B1 minus A1 squared, B2 minus A2 squared, B3 minus A3 squared. And I think I should say also that, I don't think I mentioned this, but, if vector A is A1, A2, A3, if you want to find the magnitude of a vector in R3, it's just like R2. It's just 3D. It's just a 3D Pythagorean theorem. The root of A1 squared plus A2 squared plus A3 squared. So as I've said, it's all the same. You just now have a Z coordinate as well. What I don't have in this video lesson is examples of, say, adding two vectors in R3. You guys are well practiced with vectors in R2, so I didn't think I think the video would be very long if I did examples of each of these operations. So they are contained in this practice. You're doing a lot of those basic operations you did in R2, adding a third variable. So if this seems like a lot, if a lot of these questions are just getting you practiced using these operations in R3. So if you get the idea, then just don't do them, right? In the next couple of lessons, we're going to actually talk about something called the vector product or cross product of two vectors. And so doing this work will get you well set up for that. All right, that's it for today, guys. Hope you're staying well. Have a great day, and we'll see you soon.